Have you ever pondered the ticking of time in the early universe? How does it correspond with our present understanding of time? The gravitational intensity of the early universe surely should have influenced space and time, right? To comprehend time in the early universe, we must delve into cosmology and general relativity. In the broad strokes of general relativity, gravity is perceived as the distortion of spacetime by mass and energy. This implies that the existence of massive objects can indeed tweak the flow of time. In the dense, highly charged environment of the early universe, particularly near the Big Bang, space-time would have been exceedingly curved or warped, altering the progression of time. However, when cosmologists discuss the age of the universe or timelines in the early universe, they typically refer to time as observed by a comoving observer. This hypothetical observer is stationary relative to the expanding space of the universe. This notion permits us to discuss the age of the universe in a way that's significant across diverse locations in space, regardless of the local warping of spacetime due to gravity. Thus, in the very early universe, time is gauged in terms of cosmic time, which is the time experienced by a comoving observer. This is the global time coordinate that cosmologists utilize to portray the evolution of the universe as a whole from the Big Bang to the present. Cosmic time is predicated on the assumption of a homogeneous and isotropic universe on large scales as described by the Friedmann-Lemaitre-Robertson-Walker metric, a solution to Einstein's field equations of general relativity. The cosmic time at any given instant, including the very early universe, is indeed comparable to our current experience of time. It is a measure of the duration between events along the world line of a comoving observer. However, the effects of extreme gravitational fields, like those near black holes or in the very early universe, mean that time would flow differently for someone in those conditions compared to someone in a region of weaker gravitational fields, like Earth's surface. For instance, closer to the Big Bang, the universe was much denser and space-time was extremely curved. Theoretically, if you could place a clock near a region of extremely high density and compare it to a clock in a less dense region, the clock in the denser region would tick more slowly due to gravitational time dilation. Indeed, the gravitational effects of the early universe would warp space and time. This warping is described by the theory of general relativity. However, because the universe was nearly uniform at large scales after the Big Bang, the concept of cosmic time can be applied fairly uniformly across the early universe. To wrap up, while the local flow of time in the early universe could be influenced by extreme gravitational fields, cosmologists employ the concept of cosmic time to provide a consistent measure of time's passage from the Big Bang to the present. This cosmic time is comparable to our current time in the sense that it allows us to construct a chronological history of the universe that aligns with our observations and physical laws.